Okay, welcome back. The last couple of sessions now we've been talking about problems that involve Newton's laws of motion. And primarily what we've been doing is using Newton's second law of motion, which is F net equals m times a, mass times acceleration. And of course then acceleration equals F net, or net force, divided by mass. And net force can also be calculated, though, by taking the sum of the forces acting on an object. And what we've been doing to solve problems is to make those two equal so that we can find the acceleration. Well, this time we're going to add one more little twist into the mix. We're going to talk about inclines, inclined planes. And inclines, better known as a ramp. Okay, and you've all seen those before. Okay, and what we're going to do is we're going to let objects slide down ramps. You can push objects up ramps. The mathematics, the physics behind it is the same whichever way you're going. So what we're going to do in this class is we're going to talk about inclines without friction, and then in the next class we'll add friction into the mix, and that would be the most complicated ones of all that you would have to do using Newton's second law. So let's take a look at a quick review of how inclines work first, and some of the formulas and things that we would use, and then we'll look at some examples again. So let's look at it first on a level surface. We've got a 10 kilogram box being pulled across by an applied force. And in situation A, we've got a horizontal surface. And if we want to draw a free body diagram, it's actually pretty easy to do. Okay, a free body diagram for this guy right here would look like this. Force of gravity. You always have force of gravity. Okay, so we can label that one Fg. So I'll do that. Then we also have a normal force. Anytime an object rests on a surface, the normal force always goes perpendicular to the surface. So we'll call that one Fn, or F normal. We've already got the applied force drawn in there, so I'll just extend it a little bit so it goes to the center of the object. And that's it. We're going to assume no friction here for now. Like I said, next topic we'll look at the friction as well, but right now we're going to say no friction. All right, so that's the free body diagram for case A. Now case B, the object is on a ramp. Well, the same forces still apply. Same forces still apply. So I'm going to extend this applied force in there again like that. Now it goes from the center. We still have force of gravity, and force of gravity is always straight down. So there's our force of gravity. It's the same force of gravity we had for the horizontal one. No difference. Okay, and the normal force, we still have that as well. But remember, normal force, normal means perpendicular. It's perpendicular to the surface. So that means that our normal force is not straight up anymore. It actually goes in that direction, which is perpendicular to the surface of the ramp. That's the surface that the box is actually resting on. So I'm going to call that one Fn. So obviously, when it's on an incline, it's a slightly different set of circumstances. And it's going to require some different ways to solve this. It turns out that all we've got to do, remember that this ramp is always going to be at an angle. And because the ramp is at an angle, that means that the force of gravity is also at an angle to the ramp. But all the other forces are either parallel or perpendicular to the ramp. And that's the key when we deal with ramps. What we do is, instead of using an XY coordinate plane, right, like in case A, we'd use the X and Y axis. The Y axis being the vertical and the X axis being the horizontal. But in case B, that doesn't work very well, because if we did that, the only one that would line up with our axes would be FG. Everything else is going to be at an angle to our axes. So it would be easier if we just switch some stuff around. And what we do is we rotate our coordinate axes. Instead of saying X and Y, what we're going to say is this guy right here is perpendicular to the surface of the ramp, and this guy right here is parallel to the surface of the ramp. So what we're going to do is we're going to change all our forces so that they are either perpendicular or parallel to the ramp, one or the other. Okay, one or the other. So let's look at what that involves. So the object on a ramp has the force of gravity straight down. Now we can forget about the force of friction right now. If this block was sliding down the ramp, then the force of friction will be there. Okay, we're going to do the math behind it right now, but we're not going to do any examples just yet involving that. We'll save that until next time. All right, so gravity pulls straight down. Fg equals mg. Now, the thing is, that force of gravity actually has two components. Just like when we launch an object at an angle, like when we talked about projectile motion. We found the components, the x and y components. So because this time we're not interested in x and y, we're instead interested in parallel and perpendicular, now we're going to use parallel and perpendicular components. So the parallel component of Fg is nice to know because that's the force that's pulling that object down the ramp. The parallel component of gravity. Gravity is the only thing pulling that object down the ramp. And it's the parallel component that we're interested in. So let's take a look at what that looks like. Okay, now we've got two vectors drawn here. Now this is not a free body diagram anymore now, by the way, because the Fg parallel that you see right there, that is not an actual force. It's a component of this force. So we don't actually include it in our free body diagram. We only include the actual force, which is gravity. But gravity is more useful if we break it into components. So what we're going to do is this brown vector right here, the force of gravity, has a parallel component. It also has a perpendicular component. That means parallel to the ramp and perpendicular to the ramp. So what we're going to do is we're going to use a little bit of trigonometry to change those forces, or this force I should say, the force of gravity, into components, a parallel and a perpendicular component. So using a bit of trigonometry, if this is my angle, and this is the same angle that would be down here for the ramp measured to the horizontal, that angle is also right here. It's almost like taking your ramp and flipping it around. So if we look at this angle, F parallel is the opposite side, and Fg is the hypotenuse. And opposite over hypotenuse is the sine function. The sine of any angle is the opposite side over the hypotenuse. So you got Fg parallel over Fg. If I rearrange that, I get Fg parallel equals Fg sine theta. That is always the expression that we use to find the parallel component of gravity. We always multiply the weight, which is Fg, or m times g, by the sine of the angle that the ramp makes with the horizontal. So that's where that expression comes from. Now, the best thing for you to do is memorize it, because I can guarantee you're going to need to know that expression on your public exam. So you may as well memorize it now. Second one, if there's friction, then we need to have a normal force. So in order to find the normal force, we use the perpendicular component of gravity, because that one acts perpendicular, remember, just like the normal force did, right? So to find that one, that's essentially this side of the triangle right here, which means the adjacent side. So I got adjacent over hypotenuse, which means Fg perpendicular is the adjacent side, and the original force of gravity vector is the hypotenuse. Cross multiply and you get that expression. Fg perpendicular equals Fg cosine theta, which is the same thing as saying mg cosine theta. That's how you find the perpendicular component. That's useful if you need to find the normal force. And the main reason you would need to find the normal force is if you need to find friction. And friction, remember, is just mu Fn, the coefficient of friction, multiplied by the normal force. Okay, so to put all that together, like I just said, the normal force and the F perpendicular, they're equal. The normal force there now is in blue. So here's all the vectors put together. Look, everything is here. Force of friction, force parallel, which is Fg parallel, F perpendicular, Fg, and Fn. Now, Fn is equal to F perpendicular. So we can also call that mg cosine theta. Just like F perpendicular was mg cosine theta. The only difference is the direction. Now, friction is not written in here yet because we're going to get to that next time. Okay, the next session, topic 8, will cover what we do when there's friction in these situations. So here's a summary. Here is a summary. This is what it looks like. If you have friction on a horizontal surface, you just say mu Fn, which would be mu mg, right? We got Fg equals mg. Fn is also mg, only this direction is opposite, obviously. And we got an applied force right here. This time we got an applied force pulling up a ramp. And if we're pulling a box up a ramp, friction is down. So you'd say mu Fn. Remember, Fn was mg cosine theta. So mu Fn would be mu mg cosine theta. Fg parallel, mg sine theta. F normal, mg cosine theta. And Fg perpendicular, also mg cosine theta. And you'll notice that right here we had our coordinate plane was x's and y's. Everything is in terms of x or y, vertical or horizontal. But as soon as you go to a ramp, what you do is you take your coordinate plane, your x and y coordinates, and you rotate so that it's now perpendicular and parallel. Perpendicular and parallel to the ramp surface. That's the way we look at these. That's the easiest way to do them by far. So everything then, instead of x and y, is going to be parallel or perpendicular. Parallel to the ramp or perpendicular to the ramp. So there's a quick summary of how that all works. You may actually want to print that one out for yourself. Let's try a couple of problems. So we'll try some multiple choice first. These problems are very common on the public, these types of problems. So this one here, for example, we've got a 10-kilogram box accelerating down a frictionless incline, and it's moving down the ramp. We want to know the magnitudes of the parallel and the perpendicular components. Well, remember what we just said. The parallel component of gravity, or Fg parallel sometimes it's written, is just m times g times sine theta. It's always that. It's always that number. Okay, it's always that expression, I should say. So the mass is 10. Gravity is 9.80. The sine of the angle means sine of 30. And if we did that calculation, we would get 49 decimal zero. And I'm saying decimal zero because there's 3 sig figs in all the numbers we used. So right away, we know that Fg parallel has to be 49. So in other words, the answer cannot be C or D. You can rule those out right away. In order to find which one is correct, we're going to have to do the perpendicular component as well. And the perpendicular component of gravity is always mg cosine theta. So we plug those numbers in, and the answer we get for that is 84 decimal 9. 84 decimal 9. So the answer obviously has to be A. All it asks you to do is find your two components of gravity, perpendicular and parallel. And that's how it's done. You always use sine for the parallel component, and you always use cosine for the perpendicular component. As long as the angle of the ramp is measured from the horizontal, and that's the way it'll always be given to you, that's the expressions you would use. So like I said, good idea to memorize those, just like you have memorized the x and y components of a launch velocity, for example. Okay, that's something else that you need to memorize. You need to know it. Now, you can always find it using trigonometry, but if you don't want to be fooling around with that, memorize that expression and you can't go wrong. Let's try another one. This time, instead of being asked for the components, we're asked to find the acceleration. So what we need to do is we need to write an F-net statement for the system. The entire system acting as one. If we look at the system as a whole, we do not need to worry about tension, because the two tensions, because they're pulling in opposite directions, will cancel each other out in that case. But only if we look at the system. If we look at one block by itself, then the tensions don't cancel out and you've got a problem. So we're going to do it just with the system. So I'm going to say F net the overall net force for the system is going to be, there's really two forces. There's a force of gravity pulling down on this guy, and there's an FG parallel pulling on this guy. Because the incline is frictionless, there's no friction to worry about. So the F net is going to be FG plus FG parallel. Now this FG I'm going to make negative. And the reason I'm doing that is because if you thought about this whole thing stretched out in a straight line, in other words, if you rotated this one up here so that everything's in a straight line, he would be pulling to the left, whereas the other one is pulling to the right. Remember, force of gravity on a ramp, the parallel component of gravity always pulls down the ramp. No exceptions. Gravity can only pull down. It can't pull up. The tension is pulling up. The tension is pulling the 6 kilogram block up the ramp, but gravity has to pull downwards. All right, so all I have to say now is the total mass times the acceleration equals, now this FG, I'm going to call that mass 1. And the reason I'm calling that mass 1 is because I always start on the left and go left to right for my numbering. Now if you want to do it the other way around, that's entirely up to you. It really doesn't matter. And then I've got FG parallel is going to be mass 2 times G multiplied by the sine of the angle of the ramp. So all I got to do now is divide both sides by the total mass. These will cancel. And all I got to do is plug my numbers in to find the acceleration. And if I plug those numbers in, and don't forget the negative sign there, that negative sign is extremely important, you will end up with negative 4.4 meters per second squared. So obviously the acceleration is 4.4. There it is. Done. That's the way you do it, okay? And we're going to do some examples later that involve finding the tension as well. But anyway, let's try this one first. What is the normal force acting on this box right here? The normal force. Remember, when an object is on a ramp, the normal force is always going to equal Fg perpendicular, the perpendicular component of gravity, which is always this expression, mg cosine theta. So I take my mass that I'm given, I multiply it by g, which is a constant, and I multiply that by the cosine of the angle, which is 25.0 degrees. Do that, and you get this number, 66.6, which means your answer is D for this one. But that's why that works, because normal force, when an object is on a ramp, is always equal to Fg parallel, or sorry, Fg perpendicular. Always equal to Fg perpendicular. No exceptions. Let's try this one. Same type of situation. Let's write F net for this one. For this one, there's only one object, so I can't avoid the tension. So I'm going to say F net equals tension plus the parallel component of gravity. Those are the only two forces acting parallel. And the parallel ones are usually the ones we're interested in. So F net equals. Now, because the tension is pulling left, I'm going to put a negative sign there. And at the same time, it says it's held stationary. So what that means is it's not moving. Therefore, we know the net force has to be 0. It has to be. If it's moving at a constant speed or it's not moving at all, then Newton's first law comes into play, right? No net force. If there's no unbalanced force, it doesn't move, or it moves at a constant speed, one or the other. So that's the case right here. So that tells me then that if I take my tension to the other side, because the other side was just 0, so 0 plus t is t, equals Fg parallel, which is just going to be mg sine theta. So my tension is going to be mg sine theta in this case. So I plug those numbers in, 16 for the mass, 9.80 for g, 35 degrees for sine. You plug all those numbers in, multiply, and you get this answer, 89.9, which is choice B. Choice B. All right. Moving on. Moving on. Okay, similar situation, only this time it gives us the acceleration. And it asks us to find the angle this time. So let's write it out again. This one's a little bit simpler because although F net is not 0, there is only one force acting parallel to the ramp surface, and that is Fg parallel. There's no friction, there's no rope to provide tension, so there's only Fg parallel. So what I'm going to say now is F net is m times A, Fg parallel is m times g times sine theta, and what you can do with that then is cancel out the masses if you want, even though the mass is given. You may as well cancel it out. Then I'm going to divide both sides by g, because I want to get the sine by itself. That'll cancel these out as well. And I've got sine theta equals the acceleration divided by g, which is 4.90 divided by 9.80, which is 0.5 or a half. And you should all know what angle has a sine of a half. It, of course, is 30 degrees. So the answer is B. The sine of 30 degrees is 0.5. So you just do a second function sine on that to get the answer. All right. Let's try the next one. And we've already done one very similar to this. This is another one where it's held at rest, so that tells me that F net is equal to 0. But it's also equal to a negative tension plus an Fg parallel. And the reason I'm saying negative tension is because tension is to the left. It's pulling up the ramp, whereas gravity is pulling down, right? Force of gravity is pulling down this way. Fg parallel. The actual force of gravity is that way, straight down. But we want the parallel. Remember, it's always either parallel or perpendicular, one or the other. You can't have any that are at angles to the ramp. You got to change those up. Okay, so F net equals 0, which is that. So in other words, tension again is equal to Fg parallel, which is mg sine theta. You're given the mass, you know gravity, you're given the angle. So put all those in and you would get 29 newtons, which is A. Now you got to be careful, because if you had put cosine of theta in there instead of sine theta, you would have gotten the wrong answer. But the answer that you would have gotten is there. It is there, right? Because it would be 7 times 9.8 times the cosine of 25 degrees would actually equal 62 newtons. And that answer is there. So it's a little tricky. You got to be careful. That's what we call a distractor. And those distractors, those wrong answers, are designed so that they will mimic the common mistakes that students make in these types of questions. And one of the common mistakes is getting mixed up and using cosine instead of sine to find that component. So don't get fooled. Do not get fooled by that. All right, let's look at a couple of long answer questions. These are the ones that get a little bit trickier. So what we've got here is we've got a diagram that has two blocks connected together by a massless string and a frictionless pulley, and we want to know the acceleration of the system of blocks. Now, if you look carefully, you'll notice that there's a coefficient of friction right here on this surface, on the flat surface, but there's a coefficient of friction of 0 on the other surface. So in other words, the ramp itself has no friction. That makes it a little bit easier to deal with. So that's why I'm doing this one here, because we haven't done friction on the ramps yet, but we have done friction on a flat surface. Now if you look at this, the forces, and we could draw a free body diagram, but I'm not going to bother to do that. I'm going to say that there's a force, this one right here, force of friction that's opposing the motion. So the friction will be back that way. There's also a tension pulling this way. And when we come down to the other object, there's a tension pulling on that one, which is equal to the other tension, but opposite in direction. But there's also a force of gravity parallel pulling that 8 kilogram block down the ramp. Okay? So that means that if I put it all together, your two tensions are actually going to cancel out. If you look at the system together, your tensions cancel. So just watch it the way this is solved. First thing you say is F net equals MA, okay? And F net also equals the force of friction and the force of gravity parallel. But the force of friction is negative. That's why you see this negative sign right here, okay? So FG parallel minus FF. I could have just as easily said negative FF plus FG parallel. It doesn't matter. And the mass you're looking at, because we're looking at the system, the mass is going to be the total mass, mass 1 plus mass 2, times the acceleration. So that's where that expression comes from. For this particular question, you would have gotten 1 mark just for writing that statement right there. Just for writing which forces are used and recognizing that you had to use the total mass. Okay, the expressions for those, well, FG parallel is mass 2. Remember, the one on the right I always call number 2. So mass 2 times g times sine theta. And this guy up here, mass 1, is on a flat surface, so I don't need to include any angle. I just say mu m1g, mu mg, mu fn, right, for friction. Mass 1 plus mass 2 times acceleration. There's your expression. Fill in the numbers. Okay, for filling in the numbers in this question in the right place, you actually got another mark. And then a half a mark for the actual answer, which turns out to be 1 decimal 7. 1 decimal 7. Now this particular one had an extra twist, because this was the question on that particular exam that was designated for science and communication marks. Remember I told you in an earlier class that there are 3 questions on your public exam that are designated science and communication skills. And what that means is, on that particular question, there will be an extra mark assigned to it, and you'll see the actual marks there, but you won't know. Usually the science and communication one is going to be worth 4 marks. Not always. Sometimes it's 3, but it's always 3 or 4. And that means there's an extra mark. And that extra mark is broken down as a half a mark for having the right number of significant digits, which in this case was 2 significant digits, because all the numbers you were given, you notice, had 2. Except for this one here, which is just 0, but 0 is considered an exact number when it's by itself. So we don't count it for significant digits. Not when it's by itself like that. Now when it's in a number like this, in a decimal number, it counts. If it was before the decimal like it is here, it doesn't count, because that's just there for decimal placement. Okay, so a half mark for the right number of sig figs, and the other half mark would be for the correct units, which for acceleration is meters per second squared. Now a lot of times it just asks you to calculate the magnitude of the acceleration. That's almost always what it says. Even when it doesn't say that, that's usually what they're looking for. Okay, so that is a pretty typical question from a public exam. The only way that sometimes gets changed up is sometimes they'll move the frictional surface from here to here. Sometimes they do that. Or they might have this object here hanging over the edge and this one here on an incline with friction. And next class, the next recording, we'll actually look at one like that. All right, let's do another one similar to this. Okay, same type of idea. The incline is frictionless. The incline is frictionless, but there is friction on the horizontal surface. So it's exactly the same thing as the one we just did. Okay, we still have a force of friction pulling this way, like that. We've got a tension right here. We've got a tension right here, and we've got an FG parallel right here. Now if you wanted to draw a free body diagram, you could, but you don't have to. And again, the tensions actually cancel out here because we look at the system. Anytime you're trying to find the acceleration, you have to do the system first. Now this one, it doesn't ask you to find the system, or it doesn't ask you to find the acceleration, but you need to find the acceleration before you can find the tension. So take a look at the way this one is solved. First thing we do is we write an expression to find the acceleration. F net equals ma. F net is going to be FG parallel minus FF again. Now I know it's a little small here and harder to see, but that's the only way I could fit it all on one screen. Okay, so you get a half mark for that expression, 1.5 marks for plugging it in and solving to find the acceleration. So you'll notice that the minus sign right here, that is because friction is to the left. It's opposing the motion. That's why we're subtracting. And you had to recognize that when you're talking system, you always use the total mass of the system. So you had to do that first, because if you just isolated one, you wouldn't be able to solve for tension yet because you wouldn't know the acceleration. So you had to find the acceleration first. And the acceleration was 1.3 meters per second squared. Then once you found the acceleration, then you isolate. Then you isolate one of the blocks. The easiest one to use is probably the 9 kilogram block because there's no angles involved with that one. It's only horizontal. So if we did that, we'd say tension minus friction, because tension is pulling to the right, so it's positive. Friction is pulling to the left, so it's negative, equals F net, which is MA. Okay, so tension then equals F net plus friction. Plug your numbers in, and you will get the answer, which is 25 newtons for your tension. And it only says magnitude, so you don't worry about direction. The tension in that rope, or in that string, is 25 newtons. Now, if you had done it using the other block, you would have gotten exactly the same answer. The only difference is it would have been negative, because that other tension for the 7 kilogram block would have been to the left. So you would have gotten a negative 25. But it's the same answer. It's the same magnitude. Magnitude is all you're looking for in this one. And that concludes this session. The next session, what we're going to do is look at what happens when you have friction on the incline. What happens when there's friction on the incline. So again, good luck with your studying, and join us again next time.